reason why the egg scenario is so strange can really be traced back to what's called the initial conditions of a physical system. And so it's because the initial conditions were such, arranged in such a way that it was in an ordered state, and subsequently the disorder increased. But the problem with this is that you then end up tracing it all the way back to the start of the universe. Yeah. You end up having to say, why was the universe in an initially ordered state? And for this, we don't have any answer. And so I did some work with the hour of time where we looked at the effects of quantum mechanics on the hour of time. And when you have strong levels of correlation or entanglement, then you can get reversals of the hour of time. And so you dissolve or distort the usual direction. And so I suggested that in the very, very early universe, the system must have been highly entangled to a very quantum regime. And in a highly entangled condition, you don't have thermodynamic arrows. And so the question is whether when you approach the Big Bang, does the direction of time dissolve away? And so there isn't a forward direction to time or a backwards direction to time.
Difficult to grasp on that.
Yeah. I mean,
how can you experiment this hypothesis, or is it just more of a theory and philosophy?
Well, the experiments are. When it comes to thermodynamic arrow, basically we see experiments of it every single day. Yeah. Basically, the functioning of cars or planes or people themselves are examples of thermodynamics and directionality. And a famous point is, well, why do we need the sun? What good is the sun? Well, we don't need the sun for energy. And that's because the Earth absorbs the same amount of energy as it spits out. If it started accumulating energy, it's been around a few billion years, it would have melted by now. So just from that observation, you know the Earth doesn't need the sun for energy. What it needs the sun for is order or low entropy energy. So it's the type of energy. In the same way, why do we eat food rather than rocks, stone? It's the type of energy which is important.
And low entropy energy is
useful because there's a thermodynamic arrow which runs things forward. So in that way, we have experiments all the time. But quantum mechanically, you need to work a little harder. And there have been experiments done which people are starting to build miniature motors in the quantum regime which obey thermodynamics. So this is the stage of that now.
How did actually build a small motor? Quantum motors. Do you know?
You probably have to talk to experimentalists for this one. Yeah. Technologically, it's a major challenge just to control such fine systems.
So you're looking at maneuvering individual atoms.
Yeah. And so you can use things like setting up using optics, so using lasers and setting up kind of potential with the light so that little objects will fall into the potential. But yeah, it's a technical challenge.
I see. So you yourself, how do you contribute to technology in the world? Is it more? Yeah.
Yeah, good question. Yeah, tough question. Well, my work is very much theoretical. I'm not an experimentalist, and so I'm really coming at it from an abstract point of view, where you look at the mathematics and but thinking with a certain mentality of what can you do with quantum systems. And eventually this trickles down into experiments. So I've done work on quantum computers. So it's all abstract mathematics, but with an eye towards actual experiments and actual construction of implementations of quantum computers. So you might look at system of particles that are arranged in a lattice and cool down very, very low, and then seeing what would happen if you were to experimentally manipulate and adjust them. Yeah, so one of my papers is about just this. How can you control these quantum systems in an experimental scenario when you don't have perfect control? Or another work was connected with the productions of entangled photons from a little object called a quantum dot. And these are manipulated every day in experiments, and huge amounts of experimental work is done on this. And so the scenario is the theoretical side provides the ideas of what might be possible if we had great control, and then the experimental side tries to realize that control. And so the two present two sides of very, very different challenges. And so the theoreticians often are naive in thinking that something can be done when it just can't be done. And so it's important to bear this in mind. Yeah.
So what's the actual biggest impediment in stopping the proliferation of quantum technology? You've done all this research, but how come the experimentists can't get to grips with it?
Well, you see, it's always the case that you just can't do all the things you want to do. I mean, progress is slow because we're really operating in a very precise regime, and dealing with individual atoms or individual photons. And it's easier to write down an equation for a single photon than it is to manipulate a single photon. To write down an equation takes almost no effort. To manipulate it could take a decade of expensive equipment and thousands of hours of work.
Okay.
I think, yeah, it's another good question, because you then have to ask what pace of progress is good pace of progress. I mean, in other words, is the experimental and practical progress going well? And I think overall, actually, it is quite impressive. It's just you have to appreciate the difficulties that are faced. The difficulties are almost seem contradictory. You want to isolate the quantum systems so that they're not affected by their environment, but you also want to manipulate them and control them. And these two aspects are almost contradictory. And so you really walking up.
Uncertainty principle, where you can't measure the both position and the momentum of part at the same time. So essentially, by changing or measuring what you're doing, you're changing the effective outcome of what the system should be showing. I mean, how do you tackle that sort of problem?
Well, you're right. The uncertainty principle forbids certain types of simultaneous measurements. In other words, you can't know exactly where a particle is and how it's moving at any instant of time. But this isn't a problem because you don't need to measure position and momentum at the same time. You just need to be able to control the system in a reversible way. So in the same way as you might turn a dial on a machine, and you can turn it any way you want, forwards and backwards. You also have this type of evolution of quantum system. It's a reversible evolution. And this is a deterministic process. In other words, if you can create it, then you can take a quantum system in one state and evolve it to any other state and reverse it back to that. And so the question or the aim is very different. With the measurement, a measurement is something different. It's something which is more violent. You kind of perform a measurement and you extract out classical information. Whereas with this type of evolution, you're not extracting classical information. You're keeping everything quantum. And so you're not collapsing the wave packet, which you probably heard of collapsing the wave packet, where like the Schrödinger cat example, it's in this superposition of being alive and dead, and you open the box and it collapses into being alive or dead, and that's the end of it. So the control is not this collapsing wave packet, but distorting the wave packet.
Okay. So what exactly do you mean by distorting the wave packet? So let's just look at it metaphorically in terms of Schrödinger's cat. So the cat is both alive and dead. But when you make the measurement, it's either one or the other. So you're talking about evolving a quantum state. At the same time, you're saying you're distorting the wave packet. What exactly do you mean?
Okay. So the Schrödinger cat can be in a superposition of alive and dead, 50-50 chance. But I could come along and evolve the system so it's in a superposition which is maybe 70% alive and 30% dead. So you have to ask, well, what do those numbers mean? What 70 and 30 mean? Well, it means that if I were to look at a cat, open the box, with probability 70%, the cat will be alive. With probability 30%, it will be dead. In other words, with 70% probability, you collapse it into one state, and 30% you collapse it into the other. But the state of the cat in that superposition is a single state. It's not two states. So this is maybe a misconception. Quantum mechanics says that there are more states in nature than there are classically. Classically, a cat, either alive or dead, two states, simple. Quantum mechanically, there's an infinity of states it can be in. So you've got from 2 to infinity. And each, if you pick a single quantum state, which is a superposition, it's not that the cat is alive We just don't know. Nature completely different, and so that they're the states we're interested in, forming and controlling those states.
And those states will have certain probabilities.
So the probabilities refer to when we try and look at the state through the classical lens. Maybe I'll give you an example. Okay. Suppose there are two towns in the world. There's one at the North Pole and one at the South Pole. And these are the places people live. You either come from the North Pole or the South Pole. That's the end of it. And so you meet a person and they say, I come from London. And you go, what's that? Is that North Pole or South Pole? They go, no, I come from London. And the person said, look, I don't understand what you mean. You're either North Pole or South Pole. Just give me the answer. And the person goes, okay, this is kind of confusing. Well, London's closer to the North Pole than the South Pole. And so in order to translate where I come from into this person's way of thinking, it makes sense to say, okay, I come from the North Pole, if you come from London. The person asking the question can't conceive of any other place besides the North and South Pole. But the person from London collapses either into a North Pole or South Pole state. And actually, the analogy is closer than you think, because the smallest system, quantum system, is a qubit, quantum bit. Classically, the smallest is a 0 or 1, left or right, an A or a B. And if you combine all the quantum states that are allowed for a qubit, it actually forms a ball, a sphere. And every point is a different state.
Right, okay, I'm moving to the next question. So, as it's a recent development is, like in the last 15 years that quantum physics for year rose, you must get many controversial hypotheses from your peer scientists and researchers. So how do you approach these new findings, and how do you communicate effectively with your peers?
So, controversial.
Against your...
That's a good question. Oh, how many questions are I don't want to take up all your time. Okay. That's a good question. I suppose controversies fall into three categories. One, the person is just a bit crazy and really thinks that they can solve quantum gravity, not using all this fancy mathematics, and they've drawn pictures to show it. Okay, that's the first type. The second type is where someone is saying something which is maybe a bit provocative, and what they're saying might have a flaw in it, and they're really skipping over details. And then the third type is where a person's saying something dramatic and they're right, but just people haven't understood their argument correctly. And so for the second and third examples, I can think of explicit examples. I did some work on the thermodynamic arrow at the time, and there's this fairly interesting idea by another guy who's in MIT. And it got lots of media attention, and it was on the internet a lot, being discussed. And it was a bit controversial. And basically I found a flaw in his argument, which was a technical flaw. And so this controversial claim ended up being something which was a technical mistake, which was unfortunate. And it's really impressive when in science someone can say, okay, my work is wrong, and go, hands down, that's great, yeah, and it's really, really admirable. And then the third type of controversy, which was a dramatic one, where it is correct. A PhD student here in the group, Matt, recently put out a paper on the internet, which said, the title was, the quantum state cannot be interpreted statistically. And and he mentioned in a very precise way, and it's a very significant discovery and result. He's a first-year PhD student, a big discovery, which kind of reflects the newness and growth in quantum information theory, that you can come in as a first-year PhD student and do something substantial and important. And he basically showed that whatever way nature is, it can't be certain, it can't fall into certain naive categories. And so in a sense his work constrained what you can say about reality, kind of the objective reality. In other words, what's objective in the world and what's not. And so there were blogs going, these people are crazy, they don't know what they're talking about, they don't know quantum mechanics, and they just hadn't understood what he was saying, and they needed to read his paper a bit more closely. So I think there are the three ways.
I see. And how to know which research to trust and how to be critical of these sources?
So it's a bit sociological, I think. It's partially sociological, because there's so many papers that come out each day. And so when you see a prominent name put a paper out, you have greater confidence that what's going to be in the paper is going to be right. And so you make a point of reading it and taking it on board. It's really kind of a community thing where people put out their ideas, and it's the job of other people to kind of shoot them down or be critical, but it's also the job of the person selling their ideas to convey them clearly and communicate them well. So it's kind of a messy process all around. I mean, going to conferences, people speaking at conferences, blogs. There's this thing called the archive, which people put papers out like the day they're finished before sending to journals. So there are lots of ways in which people figure out what's substantial and what's not.
It sounds like the most popular physicists, basically their papers get read and understood and criticized, but not. But what about the new names of the blog? Say if they come up with something substantial, which is basically groundbreaking, essentially, but no one bothers to read their paper or even want to understand what they've written. Mm-hmm. How does a person like that go about tackling that problem?
Yeah. I think generally, if something's right, all you really need is one person in the mainstream to become aware that it's right. and then it takes off. I mean, maybe the example of Ramanujan is a good example. He was brilliant, probably, ridiculously talented. Grew up in poverty and obscurity in India. Absorbed mathematics, rederived something like 200 years of mathematics on his own. And he sent his letters to famous people, his work to famous people. And most of them thought, crackpot, what is this? Yeah. Except one guy, Hardy, who was at Cambridge, mathematician. Hardy, very, very good mathematician, saw these proofs and realized they had to be right, and was astounded, blown away. And so brought Ramanujan to England, and the rest is history. And so that was a long time ago, when there wasn't any internet or rapid dissemination of information. So I don't think it's a big problem. I think if something's right, it's not that hard to get it out there and recognized. Yeah. But if something's wrong, it's sometimes a bit too easy to litter the internet with wrong things. And so there is this filter process where people say, look, I don't know whether this is right or wrong, but I'm not going to spend all my time looking at strange stuff.
I mean, if someone's work does end up being wrong, could that basically be a career ender for some people?
So say that again?
And so if someone's work that they've published is wrong, could that potentially be a career ender?
Not necessarily, no. I think, no. I mean, everyone at some stage puts out a paper which they later realize was wrong in some way or another. And that's just how it goes. I mean, it's better to put it out and be wrong than to not. No. I think it's really not. It's more the case of as long as you get substantial things done, so things that are right, people don't mind if you also do things that are wrong.
I guess we're all human at the end.
Yeah, completely. Yeah. I mean, Einstein had all sorts of wrong things in his papers.
Cosmological.
Yeah. No, but he had more dramatic wrong things. I think there's a Wikipedia page of list of things he did. Yeah. But the thing is, it's like he produced all these amazing things that were right. And so the process he followed was one that worked. Yeah. It doesn't have to be the case that everything you put out is right.
Are there any papers that you feel are key to understanding quantum science, or that you published or your peers have published?
Understanding. So who's the audience? Because you see why I ask.
Yeah.
Because if you're an average man in the street, there's one thing. If you're like in high school, maybe there's another. If you're an undergrad, there's another. If you're a graduate or a researcher, even there are other ones.
Perhaps let's say so researchers or PhD graduates.
I don't think there's one paper. I think usually there are books that you. It's a hard question to answer because
it is a pretty broad.
Like, is it a list of you must really have to have read this, otherwise you would basically.
So, but see, there's also the issue of understanding in what way. Do you want to understand it to use it in engineering of some quantum system? Do you understand it for doing particle physics? Or understand it as a philosopher even? understanding the meaning of quantum theory and what's assumed. But there are a number of prominent books that are important, and I think they're usually the ones that receive attention in the undergraduate course.
Books such
as? So when I did quantum theory first, it was a book by Merzbacher, which is just called Quantum Mechanics. There's a brilliant book, a famous book by Dirac called The Principles of Quantum Mechanics.
Okay.
Another brilliant book. Actually, you can't go too far wrong by reading Dirac or the Feynman lectures.
Yeah, I discussed Feynman
Oh,
a few weeks ago.
Oh, brilliant. Yeah, Feynman's great. And lots of brilliant videos of Feynman online
On YouTube.
Yeah. There are lectures of him explaining quantum electrodynamics in New Zealand, which are really, really good to watch for everyone. Yeah. So Dirac and Feynman.
What's that? Feynman, is it F-I-N?
F-E-Y-N.
Yeah, something like
that.
Yeah. What excites you most in the recent development of technology in recent years? Possibly CERN could be one.
CERN definitely. So to do with research.
Yeah.
So what are the big hotspots in the world? If you're an experimental physicist, where would you want to go?
CERN is definitely a place for particle physics. Again, it's kind of a broad question. For example, there are lots of really good surveys being conducted on the microwave background, or the large-scale structure of the universe. My sister is a cosmologist as well in Chicago. She's more involved with the experimental side. And so you have lots of ground-based experiments, say based in Chile, or space-based experiments, maybe for detecting gravity waves.
Yeah, this is the one.
Yes. So again, it's a broad question and really depends on the specific area. If you were interested in quantum technologies, the groups in Vienna, for example, are doing remarkable things, or the groups in Bristol. Or Australia is also very good. I mean, I think it was the Vienna group that recently had a first working quantum encryption network across the city. So quantum encryption has been done, and you can buy it now if you want. If you're a bank and want to have security from quantum mechanics in transactions.
How would quantum encryption actually work? Do you need new forms of hardware to sort of stimulate this?
Yeah. The basic idea, it relies on this disturbance effect. In other words, if someone measures a system, if they try and extract information from it,
Wrong information.
Yeah, it disturbs. Well, more like if you and I are trying to communicate by sending data between us, you need to send the data encoded in some physical object. It's not just data; it's data embedded in electrons or photons or whatever. But then you're like, I'm going to try and eavesdrop and find out what the communication is. Well, if you measure any of the photons or the particles, electrons, going between us, it disturbs the electrons, and there are ways in which we can always detect whether there's been a disturbance.
But by me disturbing that, would that basically...
Yes, yes.
So say if a bank has quantum security and someone tried to basically hack into that, wouldn't they mess up the final?
Oh, okay. No. So really, it's really about encryption, and in order to send something encrypted between us, you need a kind of what's called a key, and the key is like a way in which some garbled message that I send to you is decrypted by you, because you have the key. Anyone receiving the garbled message just can't get anything from it. Just looks completely random and incoherent. And so I could broadcast that message on the screens in Piccadilly, if I wanted. It would still be safe, provided he's the only person with the key. So it's more the case of key distribution. And so you can do that once, and you reach a stage where you're confident you have a good key, and then you can broadcast on the screens in Piccadilly. So it's not that and I could do that many, many times. So the disturbance isn't destroying the information of interest, because the information of interest is just kind of this classical thing which you can copy as many times as you want.
Okay. So what's the greatest success in your most recent project?
Okay. My most recent project, which just finished, haven't submitted to the world yet, is with a guy in Hanover, in Germany, and I'm quite happy with it. It's what is it? Well, the space of all quantum states is very, very big, and most states we see in nature make about a little tiny fraction of all this space. So it's been called the corner of Hilbert space. Hilbert space is quantum space. And so if you're interested in physics in the world around you, you want to probe this little small space. And in order to do so, you want to develop tools specifically for this corner of states. And so just very recently, we've developed tools for quantum fields. Quantum fields are like quantum electrodynamics, electromagnetic fields, or nuclear forces, cosmological fields. And so we have a way of describing the physics of quantum fields in a precise and streamlined way, which has all sorts of very nice properties, such as something which is similar to holography. So the holographic principle is this buzzword in...
Wait, I forgot what holographic principle is.
Yeah.
What is it?
So it's kind of it's a broad term and it applies to various things. If you're talking gravity and black holes, it's really that the degrees of freedom of the black hole are all on its kind of area, its boundary. And the entropy of a black hole is proportional to its area and not its volume. So it of an object are described by its boundary features. So there's also the famous ADS-CFT correspondence, which relates a field, a supergravity model to a field theory on its boundary, perceived velocity tension. But broadly speaking, holographic just means something which looks, say, 3D, but it's really describable by a 2D aspect, or something which is 4D, describable by 3D. So that's the broad idea. But it's an important idea in physics because lots of systems display area laws. So I think, yeah, I'm most happy with this paper. But we'll have to see whether it develops or is useful. You never know.
Right. So, lastly, how do you summarize what quantum information science is to someone who hasn't heard of this? For example, like school students in just starting school. Yeah.
No, it's good. Quantum information science is really our deepest understanding of quantum theory. And it aims to understand what's strange about quantum theory. You know, what the magic is, what's the bizarreness. So it tries to understand in a foundational and almost philosophical way what it means, or why is it that nature is quantum mechanical. But on the other hand, quantum information science says, okay, that's all really amazing and remarkable and exciting, but look, we can also do things with it. We can actually create technologies. We can potentially transform the world and impact on all different areas in many different ways. In other words, how to use quantum objects for practical purposes. For example, if we had a quantum computer, it would massively impact chemistry and engineering.
I mean, say, what's the advantage of a quantum computer over a standard computer? Why a quantum computer?
So the main use for a quantum computer when we get it working, which hopefully should be sooner rather than later, will be that it can simulate quantum systems. Okay. Let me put it this way. What do we use classical computers for? Well, you can use classical computers for describing the world around you, say, I don't know, population flow of people in a city, traffic problems. It's not, it's not that you bring 1 million people into a room and make them jostle around. You deal it abstractly in the inside the computer itself. You represent it. And when you try and apply classical computers to quantum systems, like molecules, photons, the classical computer rapidly gives up. Basically because of this infinite state space property. It takes too many parameters to really describe it. But more importantly, as you increase the size of the system, things just get worse and worse. Mm-hmm. But with quantum computers, this doesn't happen. And you can describe quantum systems in a much better way.
I mean, we keep on saying quantum computer, but what exactly is a quantum computer?
When I said about distorting this wave function in a reversible way, if you can do this distortion any way you want, then you've got a quantum computer, basically. In other words, can you move the quantum state around in all possible ways? And then extract out classical information. So it's really saying achieve perfect control over the quantum system. In the same way as you might have perfect control over a wheel or a piston in an engine. You can move it around any way you want, and you have full control over that.
I mean, you say then extracting information from quantum computer, but wouldn't that mess up the system?
Yeah, I'm thinking. Yes, that's right. And so and this is fine. In fact, there's a particular paradigm that's very new that says that you can build a quantum computer using entanglement and using up the entanglement. So the entanglement is like a fuel put in a fire and burn. When you burn it, it's gone. Yeah. So you have a system which is highly entangled, and you then go and do particular types of measurements on parts of the system, and you kill off entanglement, just collapses, disappears. But depending on how you do the measurements, you end up evolving the rest of the system.
So it's the ones that it's the entangled systems that you measure. So I'm thinking of it as two separate systems. Like they're both entangled. So if you do something this, it'll happen in this. But you measure one of them, or the other one being intact. Essentially,
yes,
is what you're basically saying.
Yes, yes. So in that example, you can imagine two little spins which are entangled. If you measure the spin of this one along different angles, then you collapse this one into different states. Yeah. And so it's kind of similar to this. It's really this non-local effect where you change the system just by how you look at it, how you measure it. And so this is called measurement-based quantum computation. And it's 5 years old. So, yeah. But I think really, maybe to sum up, the quantum information theory is really trying to get at the essence of quantum theory and the weirdness of quantum theory, but in a way which doesn't depend on the physical content. In other words, you don't care what quantum system you use. It could be a quark gluon plasma encoding the qubit. It could be a photon encoding the qubit, or an electron. It doesn't matter. In the same way as writing a sentence on paper, it's on paper, but it's still a sentence. You could have written it on a blackboard or chiseled it into stone tablets. It's still classical information, and no matter how impressive computers today are, you could equally form the same computer using stone tablets and chisels. There hasn't been any advance in the underlying information, whereas quantum information is genuinely different. I think that's the big difference. Cool. Any other questions there?
I just have one last question.
Yeah.
How do things become entangled?
How do things... Oh, okay. There are different ways. for example,
I don't know why are they entangled.
There are different ways it can happen. One way, there's no entanglement, it's all classical. But when you cool it down, it goes into like this ground state.
Mm-hmm.
And very often ground states automatically have entanglement.
Okay. Because no, it's lower nature everything wants to go to its lowest energy state. So you're saying everything is lowest energy state is entangled.
But the lowest energy state of this table would be, 0 molecular motion, frozen solid. The problem is about getting it down to that temperature, cooling things down and settling it down properly. And then that's not so easy necessarily. But the ground states of a lot of systems have entanglement automatically. Or it could be a decay of a particle where something decays and splits into two parts, and they necessarily have entanglement. So I suppose all I've really said is that these instances have entanglement, but I haven't said why they're entangled. It's actually that because of this bigger state space for quantum systems, you find that most states are massively entangled in this state space. And so if you step outside the classical regime, things are generically entangled, and it's hard to avoid it.
So that's why in a normal classical world, if I do something, it doesn't change something somewhere else.
Yeah.
Okay.
Yeah. But you would expect that one part of the universe has entanglement with another part of the universe. And so it's just that if you look at it locally, you don't see the entanglement.
If you see the whole universe,
you
should see something somewhere.
Yeah, so it gets a bit strange.
Because I was watching something last night actually, and it basically said that everything at the Big Bang was essentially entangled because everything was created at once, and everything entangled. So going with that basis, everything in the universe is entangled somewhere along somewhere. I mean,
yeah, it's quite possible. It does get a bit philosophical though, because you really start asking what entanglement is and what a quantum state is.
These things aren't necessarily fully understood yet.
No, not really. And you shouldn't believe anyone who says. Otherwise.
I mean, this is really good at describing how something is going to happen, or the predictions and stuff like that. But asking what this actually is, and usually
unanswerable question.
Yeah.
Highly explosive.
Yeah. I use I think it's a Feynman quote. If someone says he understands quantum mechanics, he doesn't understand. Yeah. So, but it must be emphasized. Experimentally, we have done teleportation. They've teleported qubits between islands in the Canary Islands.
Is it more teleportation or is it more replication? So replication.
Isn't it information to destroy at one place and recreate it at another place?
It's more teleportation than replication. And in fact, quantum theory says that in general, you can't replicate quantum states. You can't clone them. So there's a thing called the no cloning theorem.
So, which created?
Yeah, which basically says you can't take a quantum state and split it into two copies of itself. But you can teleport it. In other words, you can kind of destroy it on one side and create it.
So it's that exact same...
The exact same one.
Oh, okay, so let's just say for namesake that quantum. So exactly me is going to be created on the other side. It won't be a copy of me. It'll be that same exact quantum state.
It'll be the exact same state. But this, of course, is highly idealistic. I mean, it's an ideal scenario. I mean, they've teleported qubits, basically. It always involves two things: a measurement, which collapses the wave function, and the communication of the outcome of the measurement for certain reasons, which connects with causality and speed of light. So quantum mechanics respects causality, and for example, you can't send a signal through this teleportation because the teleportation. What I mean, you can't use teleportation to transmit a message. So the teleportation happens, but the person on the other side doesn't receive a message. So it doesn't act like a channel or a connection. Because if it did, you could send messages into the past, basically. Like actually, with the neutrino story or something.
Yeah.
What's
neutrino?
Yeah.
That was going to
they're not going faster than the speed of light, but
it's something along the lines
there's some reason why.
Extra dimensions or something. So
yeah.
Like this is. I mean, what's your opinion? What do you think is happening?
I don't think it's extra dimensions, and I don't think they're going faster than the speed of light. I think it's probably something subtle, which is to do with the experimental procedure, which there could be many things, and but what will happen is, maybe next year or the year after, a consensus will arrive in which they say, okay, this is the reason why it seemed like neutrinos were going faster than the speed of light.
I mean, they have repeated the experiment, and they've been getting the same results, basically.
I think another institute repeated the experiments and didn't get the results.
It's been mixed. And some people have gotten the same results, some people haven't.
Yeah. No, I mean, an interesting comparison is with a few years ago, a thing called the Pioneer anomaly. So in 1970s, I think, the spacecraft were sent out of the solar system. Voyager and Voyager 1 and 2, but also Pioneer 10 and 11. Okay. They probed the outer planets and they met the solar system. But then a few years ago, they were monitoring the Pioneer probes, and you notice they're accelerating for some weird reason. And they're like, oh my God, Einstein's gravity relativity is wrong, because we can't account for this. And it took about 4 years before they kind of figured out what was causing the extra acceleration they couldn't account for. And it was to do with the heating, I think, of the sun, and the way the spacecraft was responding, and tough work to explain, but it was accounted for. But that doesn't get the news. The Einstein was wrong. If you say Einstein's wrong, then people will listen. But if you say, oh yeah, Einstein was right, they go, okay, I don't want to hear that.
Yeah. I mean, if it is actually true that the neutrino is quite fast to be alive, I mean, that will probably bring about physics laws at the moment, right?
Yeah. I mean, okay, it's possible that something radically new is there, but you're not going to be able to send messages into the past, for example. because you get all sorts of paradoxes. Yeah. I mean, it'd be really good if there is any physics. But, you know, have to wait and see. Everyone hopes there. Oh, don't worry, there's always so many questions in physics. And every month more form. It's not like physics is going to finish before you get there. I used to worry about that. I was like, oh no, all the good stuff will be done.
That's what I think sometimes.
No, definitely not.
I'll take you in for it.
Yeah. I mean, we don't understand what 96% of the universe is stuff, pretty much.
Oh, it's done.
Yeah. So, I think, and that's just one area. I mean, every area has big questions. Every area.
Right, that's questions for me, basically.
Right, wrap it up. Thanks a lot, David.
Okay, no problem.
It's really interesting.
Okay.
Thanks so much.
Cool. Hopefully I provided relatively clear answers to your tough questions. You definitely had me on the ropes.
Do you have any questions or comments about?
Not really. So thanks for calling by and showing me interest.
No, thank you.
It's always nice to talk to physicists.
Yeah. There are worse venues for it. But it's always good to chat to people who are enthusiastic about physics. I enjoy what I do, so I don't mind talking about it. And I usually find that people say who aren't doing science or degrees or PhDs tend to ask really good questions. I mean, people who don't know the area ask very, very good questions, and I think should be encouraged. People take for granted their ability to probe and think critically.
You can just keep on why.
Yeah. Yeah, that's true. But I'm impressed by your questions. What answers? Did you come up with questions?
Yeah, I did. I came up with 19 questions, but
on the train I just came up with a few.
Oh, cool. Yeah. Pretty cool, guys. Yeah. So you're kind of looking more towards engineering?
Engineering, yeah. So, more mechanical. I'm interested in more computer applications of engineering. More precise results. Rather than like we look from measurements.
Yeah. It's a good area, actually. And are you thinking of a particular university?
Imperial College, actually.
Yeah, cool.
I mean, I heard it's top in the UK for engineering.
Yeah.
Especially because it funds like 3 times as much more than Cambridge.
Really?
Yeah.
I didn't know that. Wow. Okay.
I mean, you got the Cambridge interview as well.
Oh yeah. It's on Wednesday.
So what would you do if you had to pick between Imperial and Cambridge?
I would be really indecisive. I wouldn't know which one to pick.
Cambridge is an interesting place. Yeah.
I mean, you can always go one place you can do your postcard somewhere else, and then if you want to do masters in engineering, I guess.
Yeah. Cambridge it's a small, strange world. It's very unusual. But lots of famous people go around it.
Yeah.
I don't know. Imperial seems pretty cool as well. I know. I think either, Durham, Oxford, Cambridge.
My only beef with Imperial is it's in London. I want to get out of London.
Oh, right, okay.
Yeah, that's the only reason why I didn't apply.
Yeah, no, that makes sense. Yeah, it's good to go somewhere else. Actually, I think, if possible, at some stage, living somewhere else would be good.
Yeah, going to the other side of the country.
Yeah, I know. I mean, I really enjoyed it when I came to England for my PhD. It was very cool. And, then I spent a year in Sydney, actually, just before coming here. That was really cool. Yeah, physics on the beach.
Really?
Yes.
That's cool.
30 degrees.
Christmas so practical.
Yeah, really strange seeing. You're going around shorts, t-shirt, and then Santa. You know, it's like Christmas decorations.
Really cool.
But I wouldn't stress too much about decisions of what to do. Just work away on what you enjoy.
Absolutely.